Welcome to my next session in my Data Science with Mathematica track. Today I will be talking more detailed about a core feature of the Mathematica system that every data scientist absolutely needs to be familiar with, and that is parallelism, or it's commonly called concurrency from the application perspective. It's more parallelism from the programmer's perspective. Parallelism is absolutely essential for the modern day scientist, simply because we are dealing with so much data and so much computation that we cannot solve our problems unless we divide them into proper sub-problems that are independent of each other and then submit in parallel computations. And I encourage you to get familiar with a pipeline analogy from the beginning. It is very useful to think about all the jobs that you're going to submit in parallel as jobs that you schedule properly on a pipeline architecture. So I hope you see plenty of parallel pipelines here, and this is a type of mindset that I think is extremely powerful conceptually to think about parallelism and to harness the parallelism features properly. Now, before I continue, I also emphasize that in parallel right now, I also start another track about financial option pricing theory. You will find playlists about financial option pricing theory completely done in Mathematica. Okay, so let's jump right in it. I will begin my parallelism session today with some theoretical preparations, and then we jump right into the features that the Mathematica system provides us with. So I think a very important thing to understand from the beginning is Amdahl's law. And Amdahl's law tells us the maximum speed up that is possible due to parallelism. So this is the maximum speed up. This is not some average speed up or some expectation of a speed up. It is the maximum that is theoretically possible. And all parallelism incurs at least some degree of management overhead, and it may be insignificant compared to the overall gains of parallelism, and then parallelism seems worthwhile. If the management overhead is getting large, then it dilutes the advantages of parallelism, and it may in fact make it less efficient than sequential computation. So this is important to note. If your management overhead is pretty small, then you're doing fairly well. Then you're exploiting parallelism properly. But keep in mind, the number of independent compute units that you have gives you an upper bound of the speed up. It's an upper bound. All it tells you is that you can't expect more than that. It will typically be less, sometimes just a little bit less, then you're doing fairly well, and sometimes it may be significantly less than what is theoretically possible, and in that case something is not right with your parallelism configuration. Okay, so next I would like to point out an important distinction between task parallelism and data parallelism. So task parallelism is, I think, pretty simple to understand. You have different tasks, they're independent of each other, and you run them simultaneously. Like running the dishwasher at the same time that you run the laundry machine, right? They're different tasks, they do different things, but they can run independently and simultaneously. Data parallelism, on the other hand, is a different type of animal. For data parallelism, you do the same task, and in our case that's computation or evaluation, but with different independent data simultaneously. And in Fling's taxonomy, that would be an SIMD type of task, and that stands for single instruction, multiple data. And I'm giving you 3 hyperlinks here for you to read further details about this. And these 3 pages are your homework. That's your homework for today. Look up SIMD on the wiki, and then also 2 dedicated pages about task parallelism and data parallelism. And there's also a comparison table with further details about data parallelism versus task parallelism. It's important to understand that, and when we are talking about concurrent applications, then in computer sciences we really mean data parallelism, because here we have one instruction and we are threading that over all the data and all the computations that need to be done in parallel. But that's a single instruction. That's one function or one algorithm that is mapped over different segments of the data that you want to compute with. Okay, so a bit more detailed. Task parallelism is easy to understand and you've already been using it for years, right? You can fill your dishwasher and you can kick it off. You can also fill your laundry machine and kick it off. And you can now start heating tea in the microwave, and as a fourth parallel task, you can text someone, right? These are all 4 independent tasks. So all 4 tasks can run at the same time. Neither task needs to wait on any of the other tasks, right? We are requiring here task independence. And unless there is a task overload, for example, does your circuit breaker or your fuse blow when you run 3 applications at the same time, dishwasher, laundry machine, microwave, then you're making efficient use of parallelism, right? But if your fuse blows, then there is a dependence that destroys your parallelism, right? But if they can run independently and there's no contention on resources, in this case electricity, you can run them concurrently. If there is no independence, however, this would not work. All right. For example, another one, I just gave you the electricity problem. What if you don't have a cup available for your tea? What if you need to wait until the dishwasher is finished? Then you either have to exclude it from the dishwasher run and wash it manually, or you have to wait until the dishwasher is finished. All right. So keep in mind, parallelism always needs independence. Here in this case, task independence, because we're talking about independent tasks. Data parallelism, on the other hand, is a different type of animal. And here we have the same task, computation, but on different chunks of the data. And that can be independent rows, columns, or cells, or other segmentations of your data. For example, matrix multiplication can be done in a data parallel manner. None of the 6 elements of the product matrix needs to wait for any of the other computations. You can compute every element independently of the others. So assuming there are no I/O problems for reading the data from these 2 vector matrices, right? We have a left vector and here we have a right vector. Then all 6 computations can be done independently from those other elements, right? These 6 here, these are 6 computations, and each computation doesn't depend on any other of the other 5 computations. It means when we're doing this in a data parallel manner, then matrix multiplication can be done in O of n time, with n being the number of columns of the first matrix and the number of rows of the second matrix. And this assumes that you have at least 6 independent compute units. If that's not the case, then it's not going to work. And I think most laptops are still restricted to 4 cores, unfortunately. But I think in the future we can expect 8 and more. If you only have 4 cores, then this still applies in principle, but then that means only 4 of these 6 computations can happen at the same time. So if the number of compute units, and here think of them as cores, is less than the number of computations you need to get done parallel, then queuing or scheduling will have to happen. And that was the 4-core example that I just gave you. Then you have more computations to be done than pipelines you can submit them on, right? So you see those 6 independent computations here. So let's do some sample calculations on our own. So I'm penalizing every multiplication with 100 milliseconds and every addition with 150 milliseconds. Now, obviously, this is just for timing purposes. We would never do this in real life. So let's do it sequentially. And every one of these 6 cells here requires 3 multiplications, and then we're adding these 3 products together. And this takes 2.7 seconds, right? If we're adding this together, we have 3 times 100 milliseconds. That is for the multiplications. And then a one-time overhead for the addition of 150 milliseconds. We do it 6 times, so this will take 2.7 seconds. And you see it's a tiny bit more. This is because there's overhead involved and there's these actual multiplications happening. That pretty much takes no time, but there's always overhead, as I said at the beginning. So let's do it in parallel, and I will be talking about parallelize a little bit later today. And if we do it in parallel, then suddenly it only takes 0.48 seconds here. It should be 0.45, but there's overhead, right? We have 3 times 100 milliseconds plus 150, and all of these happen in parallel. So we don't have to add the time for doing it 6 times. It all happens in parallel. It is like saying timing wise, it only happens once because it happens over 6 pipelines. And if you do it over 6 pipelines, then the total time it takes, and that's what absolute timing returns us, is as if it had happened only once. Okay, and the ratio of this is, here we have 5.6, and ideally it would be 6, right? Let's do it again. See if we get better numbers. Ideally it should be 6, and we're not too far away, 5.61. Okay, next I want to spend some time on the pipeline analogy. So oftentimes a pipeline analogy is very helpful to understand this conceptually. Think of parallel pipelines with equal and constant throughput. So you have a certain number of tasks or items, and you can send them through the parallel pipelines. And based on the sizes of the tasks or the items, are they all the same? Are they all different? The number of items that you have, you can now schedule these tasks or workloads in a smart or in a dumb way. And these tasks, items, workloads must be independent of one another, otherwise this can go through separate pipelines. But if they are independent and you have n pipelines, then you can increase your throughput up to a factor of n if you keep all the pipelines busy as much as possible and you use proper pipeline scheduling and you try to minimize pipeline downtime. So imagine yourself being down here at the beginning of the pipelines, and your job is to schedule these tasks in a very efficient manner. You can put everything into one pipeline and submit, or you put different tasks in different pipelines and submit. And your goal is to decrease the overall processing time. And this ends up basically being a scheduling job. And you can do it a smart way, and you can do it in a not so smart way. Okay, so let's look at this further. In principle, $processor count should tell you the number of physical cores or CPUs that you have. And I emphasize physical because it can get confusing on modern-day systems. For example, hyperthreading can dilute the picture, and the number of licensed subkernels that you have may be smaller or larger than $processor count. And there's also $configured kernels, which is just the default list of kernels for parallel launchers. What you have in terms of physical cores, that is $processor count. And hyperthreading is usually a good thing, but for compute-intensive applications, think of it as math-heavy, the value of hyperthreading is very limited. In my own benchmark comparisons, there is no more than a 5% to 10% speed up if you do hardcore math. And you can check for yourself with a simple test how many cores you have on your system. It should be $processor count, but I want you to do the following test to understand this a little bit better. If we pause 12 times, my $processor count is 12, I have 12 cores on this machine, then it should take 1 second total time. But if I wait 1 second 13 times, then it has to be 2 seconds because each core can only wait for 1 second. We have 12 of those in parallel, so the 13th needs to go on one of these 12 cores that has already seen a wait job before. So as another comparison or analogy, if you have 12 cars and you drive your 12 cars on a 12-lane highway, then no car has any car in front of it or behind it. Like, they can all run in parallel. But if you come with a 13th car, then there must be one lane that has 2 cars. There is simply no 13th lane available, right? So here we can run all 12 cars in parallel on a 12-lane highway. But if I come with a 13th, there's no choice, but I have to open a 13th. I'm sorry, I have to open a second row of cars on this highway. Okay, let's look at this a bit closer. So the following takes a few minutes. It's 3 minutes when you have 12 cores, but the length of each horizontal section tells you exactly how many physical cores you have, and that's the maximum you can expect in terms of the speed up for math-heavy computations. So, for example, if I wait 1 second and I want to go up to 60, this is 5 times 12, that's why I'm picking 60 because it's 5 times 12, then it will take you 12 times 1 second, and then 12 times 2 seconds, and so forth until the last one is 12 times 5 seconds, right? So you get this stair here, and you can also look at the segments individually and you get 5 times 12. You just split these results by the rounded version of them. So for math-heavy tasks, don't get distracted by hyperthreading, configured kernels, or licensed kernels. The only thing that counts for math-heavy tasks is the number of physical cores that you have available on your hardware, and that is $processor count. So that doesn't say that hyperthreading is a bad thing, and my recommendation for hyperthreading is the number of physical cores that you have, and this is the way for you to find out, plus about 50%. No more than that for math-heavy computations, right? If your computer handles many other or non-mathy tasks in parallel, especially when you're handling objects such on a web server or a database server, then hyperthreading is absolutely great and you should oversubscribe by 100%. But it doesn't really help much for parallel math. In my experience, it's 5 to 10%, and you won't be able to get much more out of it. Okay, so your next homework is determine the number of physical cores that you have on your machine, and then compare it with $processor count, $configured kernels, and $kernel count. You should be familiar with these numbers for your system to understand it better. Okay, so next I'll talk about something important that makes your life much easier. By default, the Mathematica kernel will distribute the definitions that you use in the subkernels automatically. And this is true for all these parallel functions. Parallel table, parallel do, parallel map, parallelize. It will happen automatically. So for example, here I have a function to be evaluated remotely. I call it remote of x. And if we are now evaluating it, we see the integer factorization here, 1 times 1, 2 times 1, 3 times 1, 2 times 2, and here together with the kernel ID. And I have 12, so we're counting this downwards here. It's 12, 11, 10, 9. Okay, and you note that I didn't have to distribute remote. All I needed to do was say parallel table of my remote function remote, and the kernels got that definition, right? So the symbol definition happens automatically when you use these top-level parallelism functions like parallel table or do or map or parallelize, etc. Right? So you don't have to worry about it. It will happen automatically, so your subkernels will know your definitions. Okay, the next brings me to a very important item, that is the method option that we have, and it is a way for you to manage the load balancing. So parallel table has a method option that lets you specify which subunits to use. And the method option is extremely powerful, but one has to be very careful with it when you experiment, and I definitely recommend you start with a few small toy examples and then you scale up. It's definitely better start small, scale up, than to start big and then try to manage the big problems that you have. So sometimes you want to break up the computation in the smallest possible subunits. And in that case, that means you have a lot of dispatch effort at the beginning, a lot of collection effort at the end, and that means a lot of communication and management overhead. But it can be worth it. And consecutive items are then submitted on consecutive subkernels. This maximizes load balancing and is the most efficient way to submit smaller tasks, and it's useful for items that vary greatly in terms of runtime. Okay, so let's look at a few examples. Let's set n to 30 times 12, 30 times the processor count, and the items per evaluations I set to 1. Okay, so we have one task and we submit it on the first pipeline. Second task we submit it on the second pipeline. Third task on the third pipeline, and so forth. Right? This means we're going through all our 12 pipelines, and with the 13th job we start again at the beginning. Right? We submitted again our first kernel, the 14th on our second kernel, and so forth. And this is done automatically when we use the method finest grained. And you can see here that we have the kernels 12, 11, 10, and so forth, all the way down to 1. And here we have our tasks 1, 2, 3, 4, all the way up to 12. Now, when we're done with the 12th kernel or pipeline, the 13th task goes back to our first kernel. And we're counting the kernels in reverse, so it goes back to 12. So now we have the next one, all the way up to 26. To 24, that gets done on kernel 1. And now we need to wrap around again. So the 25th is back on 12, right? So this is clearly what we need to do in this case. And I use a color scheme that I have defined in a way here in order to show us how this is submitted. So the first one is submitted on kernel 12, just as we've seen above, and the second one on kernel 11, the third one on 10, and so forth, right? All the way down to the 12th task on kernel 1. Now we wrap around, 13 has to be on kernel 12 again, right? And I do this in order to show you with the color change that every task is submitted individually on a new kernel. Right? If you look at the box numbers, then you will see they always consecutively are submitted on a separate kernel. Right? 1 is on kernel 12, 2 is on a different kernel, 3 is on a different kernel, 4 is on a different kernel, all and so forth until we have to start wrapping around. Right? And this goes all the way down to 360, which is back on kernel 1. So you see that every column is consecutive tasks, and every row is always the same kernel. In all of these diagrams that I'm showing here today, every row is always the same kernel number. Right? The first row is kernel 12, and the last row is kernel 1. Okay, and this is very useful when you have several tasks that are not too big, but they are varying runtime length. And sometimes you have the exact opposite situation, right? And you need to break the computation into as many pieces as there are available kernels. This means the lowest amount of dispatch and collection effort. And it also means the lowest communication and management overhead. But it minimizes load balancing, which is a problem when you have a lot of tasks of different runtimes. And it's not a problem if all your tasks take about the same time to compute. So it's useful for items that all have about the same amount of workload. So let's look at that one. In this case, we have our items per evaluation to be the same as n, the total number of items that you have, divided by the processor count. And in the kernel, we specify that with a method crosses grained, right? And when we look at that, we are now getting a different pattern. We see that our tasks are now submitted by row first. 1, 2, 3, 4, all the way up to 12 are done on kernel 1. Again, remember, every row represents a kernel. But now also the 13th. So here we are really submitting a lot of tasks on kernel 1, all the way up to the 30th task, and then comes the second kernel. Now we start with the next batch, right? 31, 32, and so forth. And in a color scheme, you see that there are no color changes, right? We submit the task consecutively on the first kernel, then on the second, and so forth, all the way up to the 12th kernel, where we have the last task all on the 12th kernel, all the way up to task number 360. You see, there's no color change. So we submit a batch of tasks on the first kernel, and then the next batch. And when we're done with this, when we have submitted our 30 tasks, then we go to our second pipeline. And then we submit task 31 all the way through to task 60. And then we go to the third kernel and we are submitting 61 all the way up to 90. Okay? So this is courses grained, and that means that you're really submitting a long batch, as long as possible, that you have on the same kernel before you go to the next one. Right? Think about you going from pipeline to pipeline. All you need to do here is do this 12 times. You go to 12 pipelines and submit a long batch per pipeline. Whereas in the finest grained version that we've seen before, you're going from pipeline to pipeline and back to the beginning, right? You're basically changing the pipeline 360 times. And here you're changing it 12 times. Okay, so there is a way to fine-tune this actually, and you can schedule the task any way you want. You can specify the number of evaluations per kernel that you want, or you can specify the number of items per evaluation. Okay, so here we break the computation into at most 2 evaluations per kernel, and we're doing this with evaluations per kernel. So our evaluations per kernel then is 2, right? This is what we said. We're just saying 2 just for testing purposes or to understand how this method works. So let's just set evaluations per kernel to 2, and then we set this for the method option. Evaluations per kernel is 2. If we now make the same computation, then we will see, okay, let's go straight to the colored version, that we are submitting the first ones from 1 to 15 on kernel number 12. Again, sometimes it starts with the first kernel, sometimes with the last one. Performance-wise, it's the same thing. And now comes task number 16. After 15 comes 16, and this one now goes to the second kernel. That goes up to 30. Now we have the 31st task, right? This goes to the third kernel, and so forth. That means by 180, we're done with the first one, but we're also at the end of our 12th kernel, which is kernel number 1. So now we do have to go back to the first pipeline, and that means job number 181 is submitted on the 12th kernel again, our first one, which is the 12th one, right? And then we fill this. So we see that we have the colors exactly twice. We have a block on the left that's all cyan, and we have a block on the right that is all white, and that's because we set the number of items per evaluation to be 2, right? These 2. And that's why we are saying we have 2 per kernel, 2 colors per kernel. And that means the first one is a batch of 15 tasks, the second one is a batch of 15 tasks as well. But we are doing a second run of batches as we go through these pipelines again. And this is equivalent for you scheduling tasks in batches 24 times, right? Kernels 1 through 12, and then you do it again 1 through 12. Okay? You can clearly see there's 2 evaluations per kernel, 1 batch in cyan and 1 in white, 2 colors per row. Okay, But we can also do the opposite. In the following example, we don't specify the number of evaluations per kernel, but we prescribe 3 items per evaluation, and that's the other option, items per evaluation. So here we're setting items per evaluation to 3, and I'm just picking 3 for explanatory purposes, right? There's no rhyme or reason to pick 3 other than to explain the method. So we're saying items per evaluation goes to 3. And now if we are looking at this, again, I'm skipping forward directly to the colored version here. We are submitting a batch of 3 on our first kernel, which is 12. Okay, but now the next task 4, 5, 6, they have to go to the next kernel. Well, because we simply said we want the items per evaluation to be 3. Okay, so after 3 we have to stop. We're done with the 3, we go to the next batch of 3. That has to go on the second kernel. The next 3 have to go on the third kernel, right? And we do this until we have submitted all of them. That means our 12th kernel, which is kernel 1, has received its own batch of 3. And now 37, we have no choice but to go back to our first kernel, right? So here we submit the next 3, and the next 3, and the next 3. Okay, so that is much more kernel switching. And here's the graph. Maybe you understand that easier, where I specifically show the batches. Think of these as batches. Here's one batch that you submit on the first kernel, then the next 3, then the next 3. These go together. These are submitted together all the way down until the last one, right? We have these jobs that come in these 3 batches. That goes all the way here to the last batch of 3 is now on the last kernel. The first one ends exactly a batch of 3. Okay, so you can clearly see these batches of 3 items per evaluation, 3 cyan, 3 white, and so forth. Okay, and if we look at this closer, then that means finest grained is equivalent to items per evaluation as it goes to 1, as well as evaluations per kernel is n divided by $processor count. Okay, so let's check this as well. Let's look at these, and we see that when I use finest grained, I store the result in P1. When I use items per evaluation goes to 1, I set this to P2. And when I set evaluations per kernel is n over processor count, I call it P3. And we see that these 3 results are identical. We get a true, right? P1 is identical to P2 is identical to P3. And the method courses grained is now equivalent to evaluations per kernel goes to 1, right? Here we had items per evaluation goes to 1. Here we say evaluations per kernel goes to 1, as well as items per evaluation is now n divided by processor count. Okay, with the one exception that the kernels are numerated differently here. So let's do our 3 calculations again. And I'm now using courses grained, and it's now evaluations per kernel goes to 1, not items per evaluation. And items per evaluation is now n over $processor count. And we see that they are identical except for the assignment of kernels. So here you see that the first ones are all 1s. In the second version, the first ones are also all the 1s for kernel 1. And the third one, we start with 12. So here I can really only ask if P1 is identical to P2, and that's true. P3 is different, but again, that's only because of the kernel numbering. The assignment is the same, right? So here we go from kernel 1 to kernel 12. And that's true for P1 and P2. And in the third one, we go from kernel 12 to kernel 1, right? So the scheduling is the same. We just have the kernels in the opposite order. For all scheduling purposes, it's also the same as P3. Okay, the computations are the same. Okay, and if you use default option, then the evaluations are balanced. So when we use method automatic, then we get the whole thing in a balanced manner. Okay, this is a good idea if you just don't think you should worry too much about it. It's a bit of a mix between finest grained and coarsest grained. And in that case, you just don't have to worry much about it. In that case, we see that we're submitting the first 10 tasks on kernel 12, and then 11 goes on kernel 2. And we do this until we reach 111, until 120, and then we break around again, right? 121 is back on our first kernel. So you see that this is now chunked into 10, into a batch size of 10. And also the last one then 241 to 250. And the last batch of 10 here is 351 to 360 again on the last kernel. Again, as I said at the beginning, it's always the same kernel number per row, right? And I didn't specify anything about the break here. Automatically decides that we're gonna make this as a number of jobs per kernel of 10. Okay, so as I said earlier, calculations with vastly different runtimes should be parallelized as finely as possible. And here's an example where I have one job that takes particularly long compared to its neighboring jobs. The number of prime factors in the number 2 raised to the power of 193 minus 1 takes very long to compute. There are 2 prime factors that are very long. And it takes about 10.5 seconds here. Let's just compute those 2 prime numbers, those 2 prime factors. And the other ones are fairly fast. They're smaller primes. But here we have it's 3 prime factors, not 2. We have here 13.8 million and 2 rather large numbers. And this makes it stand out compared to the other expressions that we have. And when we compute this now, it does take a while to compute those 10.6 seconds. Let me do this again because I renamed this function to SM. It's now black again, not blue. Sorry for that. So, and here we see now that it takes about those 10.6 seconds, but look at the outputs. We have the number 195, and here is the number of the prime factors that we had and the timing results. It took 0.56 seconds for 195. And if we look at 2 raised to the 193 power minus 1, we get those 10.7 seconds. And if you look at this entire table, that's the outlier. That's the one number that stands out. And in the other ones, we see relatively reasonable, fast timing results and the output in the last column. And so this would be a task where finest grained would make the largest amount of sense, because we have vastly varying runtimes. So, okay, let's look at this closer. If we compute this now, and I'm taking the overall timing result, and then I just look at the result and then the first. So we are getting 2 outputs here, the table and the overall result. You see that the overall timing is the timing task of the longest job, right? Those 10.6 seconds, that corresponds to 193. All the other ones, they are not in this timing result. So this one long job takes the same amount of time as all of the other ones. That is because we scheduled with finest grained. And we can look at this a bit closer. We see when we look at the number of computations done by each kernel, we see that kernels 12, 11, and 10 had only one job. And that's important. The longest running job needs to be the only job on the kernel. And we see that the other ones had much more. Kernel 9 had 3 jobs, kernel 8 had 2 jobs, and here the numbers get bigger. Kernel 4 had 6 jobs, kernel 3 had 10 jobs, right? And you see them here in the pie chart, and the callout shows how many jobs they all had. So kernel 3 had 10 jobs, as we see here. Okay, what's really important here is that kernel 10 had only 1. That's the critical item here. If this hadn't been the case, then we would not have been able to get the longest running jobs timing result to be the same as the timing result for the total computation. If, on the other hand, we take courses grained here, let's do this calculation here and then look at the results, then you will see that all these in the pie chart look pretty much closer, right? Here's our table again, and suddenly we see a 1 and a 3 here, and you see that the number of jobs done by each kernel is much more balanced. In fact, all of them had 3 jobs. Kernel 1 had 3, 2 had 3, they all had 3 jobs. But this is quite inefficient, because now the kernel that took the longest job had 2 more. Why? Why does the kernel who has the heaviest computation any other burden, right? And this is why we see that the computation time took longer. We now have 12 seconds. And if we had done finest grained as we did above, it's 10.6. So this is extra time that we have, because that kernel for the 193 had 2 other jobs, namely for the 195 and the 104. They're all on kernel 1, right? That's inefficient scheduling. We get all of them about taking the same amount of time, because they all had 3 jobs, but that's inefficient, right? It's not that these are all the same jobs. There's one job that's very hard, and the other ones are pretty trivial. So in that case, giving every kernel 3 jobs is inefficient. Okay, let's look at this closer with actual individual timing results and their totals. So with finest grained, we had already seen this. Let's look at this with the timing result again, and when we take the first of this computation, we should again get our 10.6. And let's now aggregate these numbers per kernel. So 12 had 0.57, 11 had 0.86, and 10 had 10.6. These are the 10.6. You see that the overall is remarkably close, only very little overhead. Here it's 10.69, and the longest running job is 10.66, barely below. So we have only a little bit of overhead here for the longest running job. And you see here that every kernel has its own sublist, and these are the total results that we have per kernel, total timing results per kernel. And you see that these are remarkably close. So this was efficient. And if we now look at them as an entire list, then you see that the 10.6652 that we had here is a list of just one element, right? That's efficient. And the other ones have much longer lists, right? Here you see a lot of tasks on the first one. The second one has only one task, 0.8. That's in the overall scheme, that's a rather large number. The longest one, a list of one element, and the other ones are all much longer, right? If you look at these sublists, you see they took much longer, and the last one here is a particularly long one. Let's look at the lengths, and we see the important thing is that this one is 1. Everything else here is not really all that important. The important thing is that the longest running job was on 1. Okay, and if you bar chart this whole thing, I'm sorry, I happen to like the avocado colors, because they also are extreme colors. They go from black to yellow, which are quite opposites. And you can see in the coloring here how many tasks, how many jobs they had. And you see that some of these here had quite a lot. You see these gradations in the color. Now, the longest running task took 10.6 seconds, and I would be distorting the entire picture if I didn't stop it here. But let's look at the whole overall picture. Let's go to 11 and you see the 10.6 job is here and everything else had quite a lot of them. That's why you see color gradations in them. So back to 1.2 so that we can see this a little bit more. And another way to see this, and this is probably rather unorthodox, I can map a callout over this, and this provides me with labels now for all these that show exactly how many computations went into this. Now, this is not a particularly pretty graph, right? You would never show this in a business graphic, but for analytic purposes, I have the firm belief that for something to be diagnostic, a diagnostic chart, it doesn't have to be pretty. I want to see the information, and a way, I think a diagnostic chart never has to be pretty, and I think here we're seeing this. So here we see one label, the 10.6652 is here. This is the one label for the third bar. And all the other ones, they show you how many other jobs they had with small timing results, right? And this explains the color gradations here. Look how small they get in for some of them. So in the first one here, we basically see black. We see hardly any green there because the longest job is 0.55 and the other ones have plenty of zeros there. So we see hardly any green here. And we see when these numbers get a little bit bigger, like 0.11, 0.16 or so, we see a little bit more green here. So overall, I think this shows how many tasks there are and how different these lengths are, even though this is not a pretty plot, but I still think a rather diagnostic plot. Okay, so let's undo it, but I think you see the picture. And now let's do the same analysis with courses grained. So let's compute it with courses grained. And again, we should see a much larger timing result here, 12.5 seconds or 13 seconds for the first. That's the overall result, 12.7. And now let's look at this breakdown, right? And we can clearly see that the first one is a 12.7, right? That's barely under the total, right? So 12.77, really very little overhead. This is only 12.79. And well, why is this not 10.66, right? It has extra jobs to do that shouldn't be in there. And we here have the timing results per subkernel. And if we look at these totals, then the question is, why is this our long-running job for the 2 to the 193 power minus 1? Why is this not a list of its own, right? Why does it have so many other tasks? This is very inefficient, right? Because it has so many other jobs. Everything here is a bunch of lists, and every list is about the same length. So you can see how this is standing out in this sublist compared to the other timing results. Very inefficient, right? The lengths should be about the same, and they are. And if we now do the bar chart, again, we see a lot of gradations here, but the long one, again, let's go to the full length for a moment. We see that even the longest one has gradations, right? Why is this not just one number? It should be a totally black bar without any other colors in it. So that's very inefficient. We have a lot of other stuff in that computation that shouldn't be there. And again, let's make it ugly with the diagnostic callout. I map this over the results, and we can see that the first bar, look how many there are listed for the first bar, right? It's just not efficient. The 1055 is here, right? You see this as the 1055 merged together with all the others, small numbers here, somewhat larger numbers here, like 0.77, 0.56, but the 1055 is not in a list or is not in a bar of its own. We have all these other ones that really shouldn't be there. Okay, let's remove the ugliness. Back to it, but you see it, right? You see my point here that we're having when we're not scheduling properly. Now we can have the opposite case. We can have calculation with a large number of simple calculations, And they should be parallelized with as few batches as possible, right? Not as small or not as finely as possible, but as few batches. And here coarses grained is exactly what we want. Okay, so let's compute these numbers. Here we're making each kernel as full or as long as possible. And we see that we're getting very different timing results. The first one, when we're using coarses grained, finishes after 0.09 seconds. And the second one with finest grained is still running. That job is still going for only 10,000 numbers. And the next one, let's just compute the ratio. Let's just compute the ratio of the timing results. And we see that when we're using coarses grained, we're about 603 times faster, right? 603 times faster. That's an amazing difference in terms of these timing results. Okay, in the next case, I want to make the point that in several cases, parallelization is actually a big disadvantage and should not be used at all. When you have a lot of trivial operations, then it's oftentimes not a good idea to even try to parallelize. So if you compute a simple calculation here, like we take the numeric sign and we do it over a parallel table, we do that for numbers from 0 to 10,000, then we are 36 times faster when we don't parallelize, right? Here we have a table and here we use parallel table. Why did we parallelize in the first time? It was too much loss of time for the overall communication and management overhead. We would have been much more efficient if we just didn't parallelize and just used the table. There is no communication or management overhead. Okay, my next item. Please note that the distribution of expressions to be computed in parallel, as well as the collection of results, happens with sequential WSTP, and that is formerly MathLink. So both names are used by now. Many people still call it MathLink. Many people now call it the WSTP. So if a huge number of expressions has to be collected at the end, then this collection step takes longer than performing these computations sequentially, because the computation is so trivial, but you have so much overhead. So for example, let's square the first 100 million natural numbers. If we are doing this directly, then on a table we are getting a result of 4.2, and the parallel table version for this will take much longer. It will take an amount that is, well, 6.7 times. All right, it's not significantly longer, but at least with 100 million, we see a difference of about 50%, right? If we're adding 50% of 4.2, we're getting somewhere 6.7. And this problem actually scales with the number of parallel cores or kernels that is used. 100 million is still a relatively small number. But if we are using finest grain here, right, then this would get astronomical. We are using finest grain for 100 million, then this grows absolutely astronomical. You'll remember when I said finest grain mean each job is scheduled on a new kernel. Every job that you schedule, you walk from pipeline to pipeline. And if you do this, and I've done this here as a test calculation, then you're building up huge amounts of memory and the system will eventually crash. So even for 100 million only, then you're building up so much memory that the system becomes unworkable. So I have 192 gigabytes on this machine, and when I was reaching 180 or 188, I called quits. I just killed the kernel, because at this range here, there was just memory built up and the computation would still not return. So when I was going over 188 gigabytes, I just quit it and released the memory again, because the computation was useless. You can render the entire computation completely pointless if you use finest grained on a simple calculation like I squared with a large amount of numbers, right? Huge iterator here, simple calculation, finest grained. It's just madness, right? If you use coarsest grained, then you would be making progress, as we've seen above. All right, so if input and output are on the same order, like 100 million inputs and 100 million outputs, then parallelization is worth only on very non-trivial computations, and do not use finest grained. It's madness. The number of batches and evaluations is so large that you just have to schedule multiple tasks per batch or evaluation, right? So that's the moral of the story. Calculations with vastly different runtimes should be parallelized as finely as possible. That's an efficiency argument. You use a small chunk size, and especially when you have few and large computations. And calculations with about the same number of runtimes, then you should be parallelizing as coarsely as possible. Think of them as a large chunk size, and that's especially true with many and smaller computations. All right, so next I will want to talk about the inbuilt function parallelize. It sounds already like a top-level function, right? You just say parallelize of something. We don't have to get specific. Parallelize a parallel table, parallel do, parallel map, or something like that. No, just parallelize something that I give you. So the idea behind is parallelize a whole algorithm in a smart way. And the way parallelize does it, it looks at the unevaluated expression first, spread it over the parallel kernels that we have, and then conceivably parallelize the entire algorithm, right? And it does it by not expanding the ranges or iterators. That's important. So let's take this example here that we have. We want to parallelize this count, and it takes a long time, so I have already evaluated this. I don't want to waste a lot of time here, but if we are counting the number of prime numbers in the first 100 million natural numbers, then we're getting 5.8 million, and it takes us almost 10 seconds, right? In less than 10 seconds, we counted that in the first 100 million integers, should actually be natural numbers, we have about 5.8 million primes, okay? And note that the range 10 to the 8 was not expanded on the master kernel, but it was simply passed on to the subkernels in an unevaluated fashion. The range expression is unevaluated, and it's a mere 11 characters that we're sending, okay? And here I'm showing you how parallelize works internally, and I'm using parallel combine, which I'll explain in more detail in a moment. So when we say parallel combine with a hold, and again this mimics parallelize, then for this table example where we're going to a count of 12,000, then we first submit a table from 1 to 100. And this is not evaluated, right? This table expression is submitted in a held form. And then 101 to 200, and so forth, until at the end we arrive at 11,901 to 12,000. So we divide it into subranges, and the subranges then are parallelized and submitted in parallel, okay? And the result is 120 tables, that's 10 times processor count. They are submitted in unevaluated form, and it's not a list of 12,000 list elements for each subkernel. Why would each subkernel need to have all that information that it's not going to process on in the first place? So why submit it to each subkernel? So this is something that makes it much more efficient, and I do want to point out that this could never be done with a numerical only system, right? We need the symbolic power of the Mathematica system to be able to even do that. We need to be able to analyze or pre-process or dig deeper into these expressions that are to be parallelized before actually submitting them to the subkernels, right? If you do this sequentially, this will take you a minute and a half, right? So go in the kitchen and make some tea in the meantime. This is gonna take 1.5 minutes, and I've already evaluated, so we're not waiting around here. And the parallel version here is about 9.4 times faster, right? Simply by a smart pre-processing, splitting up the data into parallel parts, submitting to each subkernel only those parts that are relevant for that subkernel, ignoring everything else that goes to other subkernels. Okay, and here in the next examples, the kernels send back only one number, and we have that here with the count, right? And the count operation is additive over its subparts. So every subkernel only returns that count for that sublist that it received from the scheduler, from the master kernel. And also what Mathematica sends to the subkernels is very short. Yep, I just said this. So Mathematica is very smart in that it uses symbolic technology to send the unevaluated subranges. Okay, the expansions of the subranges now happens in the subkernel, not in the master kernel. That's what makes it so efficient. Okay, and the other parallel functions are very similar. So they're parallel map, parallel combine, parallel do, and so forth. So for example, in the next one, let's look at parallel map. And you see that with parallel map, we get the same behavior. We can use these method options. We have finest grained and coarsest grained also for parallel map, not just parallel table that I showed you earlier, right? We get the same results, we get the same output. Here for finest grained, we have every computation on a different kernel. That's how they are submitted. And with coarsest grained, we have plenty of computations on the same kernel before we make a break. Here we have it after 8. The 9th one now goes to a separate kernel. So we have the same behavior for parallel map as well, not just parallel table. Okay, now a few words about parallel combine. And you may be familiar with this conceptually from other languages. There is in parallelism oftentimes a combiner operation at the end. And that can sometimes also be called a reducer. That's where map reduce comes from. We first map out, and then at the end we have to reduce everything again in order to collect the information. So this is sometimes called a combiner, sometimes it's called a reducer. And the default combiner in Mathematica is join. So these two commands produce the same output. So a join is a combiner we can leave out. And parallelize is also smart enough that it picks the proper combiner. So here we get the same output, both with parallel combined together with join, or simply saying parallelize. Select is a function that parallelize knows how to break into subparts. Because we have a list, we can break that into sublists and then use select on these sublists. And then for the reducer operation, we use a proper combiner or proper reducer. So we have the same result here in these two cases. So you remember the example that we had earlier that computes the number of primes in the first 100 million natural numbers. And if we perform that operation, then again we are splitting up the range of 100 million for the count operation, and parallelize will give us the proper combiner or reducer. It takes us 10.2 seconds to get these 5.8 million. Well, let's use a different combiner. We can get the same by simply making plus the combiner operation. We can simply do this adding task at the same time with a combiner. So we compute this count in the subkernels, and then when all these results from these 12 subkernels are ready, we just add them together because count is an additive function. So we can simply use parallel combine with plus instead of parallelize. It should be the same thing. It should be the same result. There's not going to be anything earth-shattering here. We get the same timing result and we get the same computed result. Same time and the same 5.8. Okay, a few things to keep in mind with parallelize. Pretty smart actually what's happening there, and the next example will show that. So parallelize cannot always evaluate its argument to check if it can be parallelized, but it can still peek inside. It can still look a little bit closer at these unevaluated expressions in order to understand them and then still parallelize properly. So let's take a list of the first 12 natural numbers, and in the following example here, parallelize times applied over list. Then if it were to expand times applied over list, then it would be counterproductive, because then we'd have the same big list in the master kernel, right? But we don't want to have the big evaluations in the master kernel, and we don't want to have this big list. But what I'm going to do with that? Now breaking it apart is pointless, because we have already expanded it. And what would the parallel task even be doing? Deciding how parallelize would be difficult, and then parallelizing would be completely pointless. What will we do there in the subkernels? There's nothing to do anymore. So parallelize simply ignores the times for a moment, and it knows that it can parallelize the list, right? We have a list here, and then simply submits times to be applied over a sublist, and we get the same result, the 479 million when we have this result. Obviously this is just 12 factorial, but we're not interested in the actual computation here. We just want to use this as a simple example to understand the mechanisms behind. Okay, next, if it cannot evaluate the expression in any sensible way and therefore cannot parallelize at all, it simply evaluates sequentially. You get a message, but it's not the end of the world. It just means I couldn't parallelize it, and so we're just proceeding with sequential evaluation. It's not the end of the world unless you really depend on it, but then you need to restructure your code. You cannot expect parallelize to parallelize something that it doesn't understand, and you see that everything here is still blue. F is unknown, it's undefined, ABC are undefined, so how would parallelize know what to do here? So it simply proceeds with the sequential evaluation, and that is f of a, b, c. All right, and you can always look up all functions for which parallelize can pre-process the expression before submitting by looking at parallel back developer back $parallel commands. And here are these commands over which you can use parallelize. I think done fairly smart. These are top level functions, and parallelize is able to understand what function is being called, which function it is supposed to be operating on, and then properly parallelize this into the subkernels. All right, so next I'd like to spend some time on parallel submit. And parallel submit submits for evaluation on the next available subkernel, and the return is only for the time being an evaluation object that represents the submitted evaluation. Not the result yet, just the submitted evaluation. And the submitted computation will not start before a wait command has been called. This is similar to what you may be familiar with in other programming languages that run on virtual machines, like in Java or in C#. This is no different. You need to wait until you get a result, and it's the wait that even triggers the computation. Without a wait, the computation doesn't even launch. Okay? And this is great to watch the scheduling or computation activity live. So let's take the factor integer task from above. And again, we're interested in 2 raised to the power of 193 minus 1. We're starting with 195, counting down in steps of 1. So we should expect the third one in the list here to take the longest. And you see this one is still running. The other one's already finished. But 2 to the power of 193 minus 1 takes the longest. And here are all the results. We're not interested too much of them. We know that the case with 193 returns 3 factors, 3 prime factors. We knew this before, but again here with this type of display with parallel submit, we can see which one takes so long, which one is the offending computation that takes so long, which one is the computation that's still not done yet, which is the computation where we can maybe still make further improvements. All right, this is a visual way to look where are we still spending our compute resources on. And again, I make the point, parallel submit only submits, it doesn't trigger the computation yet. So here, if we are triggering a computation with parallel submit, if we are submitting a computation with parallel submit, but don't trigger the computation yet, then we see that all of the above are still in light blue. That means ready for processing, but no computation is launched yet. We have to trigger the computation with one of the wait commands. And here, let's submit with wait all on the evaluations. And here we see they submit and number 3 is still running. So once we've done this and once the last one finishes, then we get the result. And here we have, again, with 193, it takes 10.7. The result is 3. We have 3 prime factors. Okay, so next one, I want to show you that wait next is a command that returns 3 outputs. It's a way to step through the outputs. And let's pause for 5 seconds, 10 seconds, 15 and 20 seconds so that we can see the progression. So here let's submit them. We want to have 5 squared, 10 squared, 15 squared, 20 squared, but we always wait the same amount of seconds and we want to see how this progresses. So we have 4 list elements, so we use wait next 4 times. Okay, so as we submit this, we see now the first one we now see that everything is running. And the first one finished after 5 seconds, the return is 25, and we have 3 remaining. Here's a list of 3 remaining. Next one, we take the first element, and there's a sublist of 2 remaining. Next one, we have the first one, and there's only 1 remaining, and eventually we get the last result, and the list of remaining items is empty. Okay, so let's do this again. Let's submit it and watch the progression. So we have 4 computations. Right? We always have the first one and the list of remaining computations. So here we have 3 in the list. Next result, 2 in the list. Next result, 225, 1 in the remaining list. And the last one, 400 and nothing remaining in the list. Okay, so wait next is a way to consume computations element by element, but it's important to really return 3 elements and store them that way. Otherwise, wait next is getting confused. We are not able to really see how this goes forward. And scheduled evaluations no longer need to be aborted when we're using abort kernels. So for example, let's submit this computation, and here now I'm waiting 205 seconds. We are not interested in waiting 205 seconds, right? We are only interested in the first computation. So let's kick it off. I say wait all on the first of the IDs. That's 25, obviously, 5 squared. But instead of waiting 205 seconds now, we have a result and we're okay with the entire parallel computation. Once the first result is concerned, we can now say abort kernels. And you see that the next computations are aborted. We get a return of $failed, and we didn't compute it because we were happy with the first result. And this is sometimes very powerful if you're just interested in the first result that comes back. If all the results from your parallel kernels are good enough, then you might as well be satisfied with the first one that comes back. You don't have to look at all the others. Right? Sometimes you need all the results. You need to construct something with them. And sometimes you just need the first result that comes back. Or the others are just as good, but not better. Right? So it's a great way to kill them then and to just take the result of the fastest computation. All right, and parallel submit and wait all is also a fantastic way to observe the progress of tasks live. So when we are submitting this, then we're now saying wait all, and here this is based on random numbers now, right? So we see clearly which one of these calculations is going fast, which one takes a lot of time. Here in this case it's the third last one. It's quite unpredictable because we're using random numbers, but we can clearly see where the computations are and where they are already finished. What's the bottleneck? Where are we stuck? Right? This is a great way to visualize where your problems are or where you don't have problems. And parallel submit is a great way to visualize all this and to also have more fine controlled control over your submissions. Which kernel does it go to and how do I see the progress? You can really use these wait commands in order to selectively step through solutions. It's very, very practical. It's very handy and gives you a lot of flexibility. So an evaluation goes through the states ready, running, and finished. Okay, so let's submit a new job where we have 6 items. We just want to square the numbers, but we want to look at the stages that we're having. And here we have now 6 in a list that are ready for processing. We didn't call any wait yet, so nothing is triggered. So let's call the first wait, and that triggers the computation, but let's consume only the first 2. We see that the first 2 have finished, the other 4 are received, but they didn't compute yet. Right? We need to wait in order to trigger those computations. And now let's take evaluations 3 and 4. So when we do this, we now have the first 4 have finished, and we still have 2 that are only received, but as we didn't call wait on them yet, they haven't computed yet. They're only received, not done yet. And let's compute the last ones, 5 and 6, and now we have all 6 that are now finished. Okay, and you have to keep in mind, and this is also just like in Java and C#, each evaluation should be waited for only once, and another attempt gives us an error. If I now wait on these EVS, on that list of the submitted tasks, we are getting $failed as returns, and we see that all these tasks have failed. The same is true when we're trying to evaluate something that was already evaluated. So here let's do it in steps. Let's evaluate only the first 2. Again, we have finished and finished for the first 2, and the other ones are received. And now I'm trying to consume the first 2 again. So here again we're getting an appropriate error message. We see that the first have failed and the others are still there. And it's pretty obvious why we're trying to consume the first 2 already, even though they have already been consumed here. But you can still consume the rest because items 3 through 6 have not been consumed yet, right? So if I take 3 to 6, that works just fine, and you see they're now finished. Okay? Parallel submit together with wait all and wait next. The important point to note is parallel submit gives you maximum scheduling flexibility, but you are responsible for the scheduling and the proper consumption of the results on your own, right? Again, great flexibility, but the control is in your hands, just like C# or Java. That's where you have to do a lot of the management on your own as well. And this is similar to what we have in other languages or platforms known as fork join or map reduce or parallel combined with a joiner operation or combiner operation. Okay, so I have 2 more notes before I come to an end. The parallel framework is not supported yet in the private cloud or the public cloud, and it won't be for quite a while. And we have additional functions in the parallelism framework for setting a shared variable, a shared function. We can unset them, we can look at all the shared variables and so forth. And I recommend against using them. because they lower performance, because a lot of communication overhead has to happen. They need to be submitted to the parallel kernels, they have to be collected again. So there's a lot of communication overhead that lowers the performance, and it also provides for a host of threading problems. It's very easy to implement threading bugs when you're using shared variables and shared functions. If you ever think you have to use them, then I recommend you think again. And if you then still think you need them, then consider if the performance hit is worth it, because it does cost performance, sometimes not a lot, but it definitely does cost performance, and you may not always want that. All right, this brings me at the end of today's session. I hope you had as much fun as I had, and I hope you see me next time, or you have a look at the other tracks that I have. Thank you. Bye-bye.